In this sort of lecture, let's consider the geometry of the complex mapping W equals Z to the power of n, where n is, we'll take n to be some positive integer. If you recall like discussions on complex functions, typically when we have to plot a function of a complex variable, we make two copies of the complex plane. One of them we call the z-plane, so let's just call this the z-plane, and the other one we call the w-plane, where the function is denoted by the symbol w, so this is the w-plane, and we label the real axis on the z-plane with the symbol x, and the imaginary axis with the symbol y, and the real axis in the w-plane with the symbol u, and the imaginary axis with the symbol v. So the idea is that this is a mapping w, which could be some function of z. And so typically we write w in the form u plus iv, which is a function of z. And here u is some real function of the variables x and y, and v is some real function of the variable x and y, where z is of the form, a complex number of the form x plus iy. And again, the idea for behind making two copies of the complex plane is that if you notice, we have four variables we have to deal with: u, v, x, and y, and there is no straightforward way in which we can sort of plot all four variables or make a simple two-dimensional plot using four variables. And that is where one of the ideas is to make two copies of the complex plane, a z-plane and the w-plane, and then consider the effect of mappings on certain figures in the z-plane and how they transform under the mapping that we're considering. So in this case, let's consider the mapping w equals z to the power of n, where n is some positive integer. And this is very extremely useful mapping, in particular if you want to analyze the geometry. Once we understand the geometry of this mapping, it's extremely useful as we proceed further in our study of complex analysis. We'll see that if we grasp the essential ideas behind the geometry of this mapping, it will also help us understand the ideas behind critical points, branch points, and some extremely useful concepts in the study of complex functions. All right, so let's get started with a simple description of how to understand the geometry behind this mapping. And for that purpose, let's consider a unit circle in the z-plane. So let's just draw a unit circle in the z-plane. So let's say this is a unit circle in the z-plane. Okay, and we'll consider the effect of the mapping. So we'll focus on the mapping f. So we'll focus on w equals z to the power of n. So our function is a polynomial function of the form z to the power of n. And we'll see the effect of this mapping on radii and arcs of the unit circle and see how they map in the w-plane. Now, when we're talking about the unit circle, so one of the ways of depicting the unit circle in the z-plane is, if you recall, let's say you're at some point z on the unit circle, which makes an angle theta. Then we know that the x-coordinate of this point is cosine theta, which is the projection of this vector along the x-axis, and the y-coordinate is sine of theta. And therefore, the complex number that this mapping represents, or the complex number that z represents, is of the form cosine theta plus I sine theta. And if we now invoke Euler's identity, then we know that this is essentially equal to e to the power of I theta. And so if you have to represent a unit circle in the z-plane, the polar representation of the complex number is a very natural representation to consider. And we'll sort of keep this in mind, and as we talk about this particular mapping, that we'll basically be talking about, or we'll basically be invoking the polar representation of the complex number z and studying the effect of this function on that polar representation of the complex number z. Okay. Now another useful thing. So for this, let's just label this circle as z equals e to the power of theta, so that it's there on the board and easy to remember. Now, one of the things that one very extremely useful analogy when we are considering this mapping is to think of yourself as taking a walk along this unit circle, and then we'll see what is the effect of this mapping as you walk along this unit circle. In other words, as you walk along this unit circle, there will be an image that will walk in the w-plane, and we'll see what is the figure or the curve that that image traces. So just imagine yourself walking on a unit circle and then see where your image lands up in the W plane. And we'll sort of talk about this mapping with that sort of picture in mind. Okay, so let's say you were to start walking at the point z equals 1. So you're at z equals 1. So the first question is, under the mapping w equals z to the power of n, and let me just write down here that n is some positive integer. Okay. So under the mapping wz equals z to the power of n, where is the image of the point z equals 1? So z equals 1, so w equals z to the power of n, and if you're at the point z equals 1, then 1 to the power of n is 1. So the image of this point is w equals 1. In other words, the point z equals 1 maps to the point w equals 1 in the W plane. Okay, now let's say you start walking along the unit circle in this direction, counterclockwise direction, and you land up at a point z, which makes an angle theta with the x-axis. So now the question is, where is the image of this point z equals e to the power I theta in the W plane? Now again, we are looking at the mapping z to the power of n. So w, which is z to the power of n, will be e to the power of I theta to the power of n, which is e to the power of I n theta. In other words, if the arc that you subtend at the origin makes an angle theta in the z plane, then as you start walking the z plane, your image starts walking in the W plane, beginning or starting at the point w equals 1, and once you've covered an arc that subtends an angle theta at the origin, your image would have covered an arc that subtends an angle n times theta at the origin. Okay, and if you continue this walk further, you'll see that if the arc that you subtend, arc that you've covered subtends an angle 2 pi over n, then your image would have covered an angle which is 2 pi. In other words, when you reach the point z equals e to the power I 2 pi over n, then your image would have arrived at the point z to the power of n, which is e to the power of I 2 pi over n to the power of n, which is e to the power of I 2 pi, which is nothing but w equals 1. So if you have covered an arc that subtends an angle 2 pi over n, let's say this angle is 2 pi over n. So let's say this is an arc that subtends an angle 2 pi over n as you move in the counterclockwise direction, then your image would have actually covered the full unit circle in the W plane and arrived back at the point w equals 1. And this is extremely interesting because what this tells us is that your image in the W plane is moving n times faster than the rate at which you are moving along the unit circle. And this is because if you cover an angle theta, your image is covering an angle n theta. If you cover an angle 2 pi over n, your image actually covers the entire circle. Let's take some specific example. Let's say n was 1 to begin with. Now that's the identity mapping. Now when n is 1, then all the images map identically to the same image, and therefore you and your image are moving at the same rate. But let's say n is 2. It means that once you've covered an angle 2 pi over 2, which is pi, by the time you reach here, your image has actually completed one entire revolution in the W plane. And what this tells us is that as you move further along the unit circle, let's say for a general n, then points which are separated by an angle 2 pi over n, all these points will actually have their image at the same point in the W plane. In other words, the point z equals 1, in our case, the point z equals 1 maps to the point w equals 1. Likewise, the point 2 pi over n also maps, or e to the power 2 pi over n also maps to w equals 1. Likewise, the point, if you move further by 2 pi over n, we'll arrive at the point which will make an angle 4 pi over n with the origin. And this point also maps to w equals 1. And for a general n, points which are separated by angles of 2 pi over n regularly are actually vertices of a regular polygon, which is inscribed in the unit circle. And this regular polygon and these vertices are all mapping to the same point in the double plane. Now, let's make this more explicit by considering a specific example. Let's say let's consider n equals 3 and see what that means. So again, we are at the unit circle in the z plane. Okay, and then we have the double plane. Now on the z plane, we have a unit circle, and we are considering the mapping w equals z cube. Let's focus on the specific case when n is 3. So you start at the point z equals 1. Your image is w equals 1. Let's say you rotate or you move along the unit circle and arrive at the point that makes an angle 2 pi over 3. By the time you cover this arc, your image has actually covered one entire circle in the double plane, and this is again a unit circle in the double plane because the magnitude of all the points here when raised to the power of 3 are still the magnitude of all those points is still 1 because w, which is e to the power of I, let's say n theta, the magnitude of this modulus of w is still 1. So all these points still lie on the unit circle in the double plane. So once you arrive at the point 2 pi over 3 or e to the power I 2 pi over 3, you've completed one revolution in the double plane. Now you move further and you arrive at the point which makes an angle z, which is e to the power I 4 pi over 3. And again, by the time you complete this arc, you've completed another circle in the double plane and arrive back at the same point. And then as you move further and cover the remaining angle and arrive back at the point z equals 1, you've completed a third revolution in the double plane and arrive back at the point w equals 1. So by the time you complete one revolution in the z plane, you've completed 3 revolutions in the double plane. And notice that all these points, once we join them together, these vertices z equals 1, z and this point is z equals e to the power of I 2 pi over 3. This point, we join it to the point z equals e to the power 4 pi over 3 to the point z equals 1. This is a regular 3-sided polygon, which is nothing but an equilateral triangle. And we see that, in fact, all the vertices of this equilateral triangle map to the points w equals 1. Now, as a byproduct of this sort of geometric analysis, you also notice that we have actually solved an algebraic equation. In other words, we have actually looked at the equation w equals z to the power of, for a generic n, equals 1. And this is because we have looked at all the points z whose image in the double plane is w equals 1. And we have looked at all the points z which actually map to the image point w equals 1 in the double plane. And what are these points? These points are nothing but the vertices of a regular n-sided polygon inscribed in the unit circle in the z plane. We can make this more explicit by solving this equation algebraically, which is, in other words, if we are solving the equation z to the power n equals 1, if we take z to be e to the power I theta, then the equation that we are solving is e to the power of I n theta equals 1. Now we know that 1 can be represented by a complex number e to the I 0 plus some positive integer 2m pi, or some positive integer m 2m pi, or rather some positive integral multiples of 2 pi. And then when we compare the exponent of this exponential, we find the solution that theta is 2m pi over n for some positive integer n. Now, how many distinct values can m take? We know that if m is n, then theta is 2 pi, which means we have arrived back in the z plane to the point z equals 1. So therefore, if m is a positive integer, it can take all values that go from 0, 1 to n minus 1. Now these are n distinct values that n can take. And these n distinct values, if you notice, let's say we pick up a couple of values for, let's say, n equals 0, theta is 0. When n is 1, then theta is 2 pi over n. When n is 2, then theta is 4 pi over n. And you notice that all these points in the z plane, which are e to the power I theta, where for theta equals 0, 2 pi over n, and 4 pi over n, are separated by angles of 2 pi over n, and therefore they lie on the vertices of a regular polygon, which is again what we found geometrically. So yeah, I hope this sort of introduction to the geometry of this complex mapping is of some use. And let's talk more about these ideas in future videos, and hope to see you there. Thanks for watching.